Okay, so here we go. Last time we had just barely scratched the surface of these symmetry theorems that we're going to talk about. Well, in fact, we hadn't even got to it, but I reminded you of the single variable symmetry theorem, and so this is something that you should have seen in a single variable calculus class if you are looking at an integral that you're interested in for whatever reason, right? And two things. If the integrand is odd, right? Now this is what odd means. Odd means that the value of the function turns negative when you negate the input. Right? Or said differently, if you flip the input over the origin, you might say if you reflect it over the origin, then the value of the function becomes the negative of what it had been. Okay, let's see here. Then, and furthermore, if the domain is symmetric. Now, here's a kind of a precise definition of what we mean by symmetric, but good news, it means exactly what you think it means, right? It means that if you flip it over the origin, right? Again, here's that idea of a reflection, reflecting over the origin, that you get the same thing. In other words, that this is an integral from like negative a to a, right? Where the lower bound and the upper bound are opposites of each other. If this happens, then your integral is 0. And the beautiful thing about this is we just computed an integral without doing an antiderivative, which is great because antiderivatives are hard. Certainly can be hard. Okay, so hopefully you all have seen this before. We're going to talk, I'm going to go back to what I just skipped in a minute. We're going to talk about the same idea now, just in 2 dimensions. And so here it is. In order to adapt this theorem, we're going to have to talk about a 2-dimensional version of a reflection, right? And so if you've got some line, the idea of a reflection is exactly what I have drawn in this picture. It's, you kind of flip over the line, if you will, right? It's just like flipping over the origin in single variable. It's just kind of 2-dimensional. And because it's 2-dimensional, we have kind of more room to move. There's more directions in which we might do a reflection. So you can pick any line, in fact, and that's actually a really powerful advantage here. So with this idea of a reflection in mind, we're going to define oddness oddness in exactly the same that we did for single variable. Odd just means that if you plug in the reflection of a given point, you will get the negative of the value of the function that you would have gotten at your original point. Exactly the same idea, right? And likewise, what do we mean by symmetry? And again, look, you can write this down in a precise way, but I'm going to say this means exactly what you think it means. It means, a Rorschach test. Like if you fold it, you get the ink goes on both sides. Another way to say it is if you flip it over the line, it doesn't change. It's the exact same shape. It's the same symmetry that you would naturally expect. And with these ideas developed, again, we have the same theorem. Here it is. If you are looking at an integral, now this is a double integral. Double integrals are even scarier than single variable integrals. After all, there's 2 of them, right, for one thing. If you were looking at an integral and if 2 things happen, if your integrand is odd, and if, color choices, if your domain is symmetric, then great news, that integral is 0. No slicing and dicing required. No anti-differentiation required. Right? This is awesome. Super powerful. Okay. All right, now you'll see the warnings that I have down here below, and really I kind of like to present this all at once as one big thing because it's really easy to accidentally screw this up, and that's very dangerous for reasons that I'll explain soon. But you do need both of the conditions, right? That's very important. Very often students will get a little overconfident, a little over-enthusiastic about the use of the odd symmetry theorem, and they'll see a symmetric domain, and they'll see daylight at the end of the tunnel, and just run for that daylight, right? And forget that you have to check and make sure that that integrand is odd. It's only a valid argument in any sense if the integrand is odd also, right? So you got to check both And it goes the other way. But sometimes students will see an integrand that they'll look and they'll see odd powers and they'll be like, hey, boom, odd, right? You gotta check that domain. Right? So both conditions have to hold. And also, very importantly and easy to screw up, it's got to be the same line for both of the conditions that you're required to check. So it is absolutely nowhere near, not even close, good enough for the function to be odd over one line and for the domain to be symmetric over a different line. That's not even close to good enough. And again, easy landmine to accidentally step on. Okay. All right, so let's talk about why this is true. I am going to move really quickly through the why because we're in a hurry, and that's not really what kind of a class this is, of course. I mean, we want to see some of the whys, but not really worry about all of the whys. Here's the sort of single variable version. I can zoom in a little bit better. Here we go. So this is the kind of picture we're talking about. You can see we have our symmetric domain here from negative a to a. So symmetric domain. You can kind of see in the picture sort of the oddness of the function, that it's sort of the exact opposite on the left as it is on the right. And with all of that in mind, notice that when you look at your Riemann sum, here's your Riemann sum, right, you can kind of pair up the terms, and let's compare this term in the Riemann sum, if you will, and this term, the ones that are sort of opposite of each other, when reflecting over the origin. Okay. And okay, well, you can see that these have the same width, so the delta x's are the same, and the whole point to the oddness is that the value of the function on the left is the negative of the value of the function on the right. So we get this equation here. I mean, if green is green and purple is purple, then boom, right? We get that equation. And with that established, now keep in mind what these things are. This is one of my terms in my Riemann sum. And furthermore, let's see color choices. This is a different one of my terms in my Riemann sum. And what we have here is that these are negatives of each other, and therefore those two terms cancel. And of course, because this is a symmetric domain, every one of these terms is paired with its sort of reflection sort of buddy over on the other side, and so all of the terms cancel, and the integral is 0. So broad strokes, I hope that makes sense. This is, again, kind of morally why this works. You can also take a point of view that's algebraic. By the way, this is why I have this discussion in the section on change of variables. It's because the way that you would show this algebraically, or sort of more formally, is by using a substitution, which, again, is basically a change of variables. It's a single variable change of variables. And if you just kind of write down this substitution, that x equals negative u, and just kind of follow it through, then what you find is that this integral is its own negative, and therefore it's 0. So this is a more algebraic approach, and maybe a little bit less visually satisfying. I find this a little bit more sort of, intuitively, viscerally satisfying. Okay, so the same ideas work in two dimensions. There is a pullback change of variables argument. You literally pull back through the reflection that we were just talking about. But again, that's more algebraic and a little bit less satisfying. Here's the Riemann sum argument, and you're going to notice it's the same argument. This piece and this piece of the domain have the same size. And oddness means that the value at the reflection is the negative of the value at the original point. So that establishes this equation. And with that noted, keep in mind that this term is a term in my Riemann sum, and this is a different term in my Riemann sum. And this minus sign means that they cancel. So again, every term, you might say below the line, has a reflection buddy on the other side of the line, and so not only do all the pairs cancel, every term is part of a pair, so all the terms cancel. Again, I find that a little bit more sort of intuitively satisfying. Okay. All right. So, yeah, big theorem, very useful. The reason I like to make a big deal out of this theorem is because of how much I used this theorem when I was in college. And again, you know, math major, fine, right? But I know most of y'all aren't, and most of y'all are engineers and similar. So hopefully more persuasive. In my physics major, I used this theorem and the three-dimensional version of it that I'm going to show you soon. Oh my gosh, so much. Just ridiculous amount. Physics majors are full of integrals. So are engineering majors. So you've got a lot of integrals in your future, right? My conservative memory estimate of how often I used this theorem and the 3D equivalent. In other words, what fraction of the integrals that I encountered were instantly zero by symmetry? I think about 20%. So that makes this arguably the single most powerful computational trick for computing integrals that I know. And so it's a big deal, right? And the way I like to phrase it is my physics major had 9 classes, and so 20% of the integrals over 9 classes is a full 1.8 physics courses worth of integrals, right? And I think that pretty impactful. It sounds like a lot because it is. Okay, so let's do one. Let's get our hands dirty. Here is the question. We want to compute this integral right here. Bounded regions bounded by certain curves. So now, of course, in order to understand what I'm even dealing with, I do need to draw a picture. Oh gosh, where's the button? Here it is. I need to draw a picture here. And so let's see here. I'm going to just kind of sneak in a quick picture over there. First of all, let's talk about this curve. Now, that's a single variable calculus thing, but hopefully y'all remember how to do that kind of stuff. And that curve looks something like this. I'm going to try to draw it decently because I'm going to be making a geometric assertion about the picture in a moment. Okay. Then there's this curve right here, y equals -1, and that's, something like that. So my region, the actual domain for this integral, is this thing in here, kind of weird looking shape, like that. And now I'm just going to make a kind of a hand-waving sort of geometric appeal that's symmetric over the y-axis. And everybody kind of see how if you sort of flip that over, it's going to be the exact same thing. Now, if you don't believe me, if you're not persuaded by the geometry, one argument you could make is you can literally write down the formula for the reflection. And so here's my reflection formula. For any point in the domain reflecting, you'll notice just changes the sign on the x-coordinate, and it leaves the y-coordinate the same. There's our picture reflecting over the y-axis. So that's my reflection formula. Is everybody happy with that? Again, a geometric appeal. I will point out one thing that is a little confusing. It's an easy sort of oops. Even though we're reflecting over the y-axis, the minus sign goes on the x-coordinate. It's weird, right? But it's a little bit symbolically counterintuitive, you might say. But that's the geometry. That's unavoidably just how it works out. Okay, so heads up, watch out for that little landmine. So with that idea, notice that if you just plug in that reflection into this equation, what you get is the exact same equation, right? The reflection doesn't affect that equation at all. In other words, this purple curve, this is an algebraic demonstration of why that curve is symmetric. It is its own reflection. And then likewise, the green line, I think it's pretty obvious, also is its own reflection. So, okay. All right. Okay. So now we've talked about the domain. Let's talk about the integrand. This is a pretty weird looking integrand that I've got here. I need to know whether this integrand is odd. Reminder, how do we decide if an integrand is odd? Well, here's our definition of odd symmetry. You establish odd symmetry by plugging in the reflection and making sure that what you get is the negative of the original value of the function. Right? So we're going to literally straight up do that. And here we go. Plugging in the let's see, I tried to get this all on the screen. Plugging in the reflection. You can see we're just going to take negative x and plug that in for the x's. So this expression, right, that being f, when you plug in the reflection, you get that, you put the negative x in that place, right? So you can see the minus x here and there and there. And now it's just kind of algebra, and you just have to remember how does the various little bits of how algebra works. This minus sign gets cubed. Cool. Minus sign comes out. This minus sign gets squared. It disappears. This minus sign is inside of the argument of the sine function, and now you have to remember, right, this is one of the symmetries of the sine function. Sine of negative x is the negative of sine x. And so that minus sign pops outside and cancels with that minus sign. Is that cool? So, okay, so we just computed something. Now, what does that have to do with our question? Our question was whether this, wrong color. The value of the function at the reflection, is that or is that not the negative of the original value of the function? So you've got to compare this to this, and are they negatives of each other? I'll just take it term by term, and yep, sure enough, they are negatives of each other. And so the value at the reflection is the negative of the value at the original point. So our function is odd, game over. This integral is 0 by symmetry. And we didn't have to integrate anything, which, by the way, thank God, right? Look at this integrand. What a nightmare, right? I'm not too scared of this second term, but that first term looks like a real pill. Yeah. Okay. Everybody happy? Okay, let's see here. Now, let me erase my mess, and I want to talk about some sort of course requirements for this sort of an argument. And I really do love this argument. It's a really great argument, very powerful, and I hope you'll use it a lot. But that said, I was a college student once myself, and I pulled the fast one more than once in my classes, and the fast one goes like this. I had an integral to compute. Maybe it was part of a larger question, and I had gotten it down to I just need to compute this integral, and there's 10 seconds left on the clock. I don't have time to mess with, so I just write equals 0 by symmetry, turn the paper in, right? And most of the time I tried that, it didn't work, but a couple of times I scored, right? So now, should I have gotten credit for what was in fact purely a guess? No, of course not. Right? So with that in mind, I do require that you actually make an actual argument. If you're going to make a symmetry argument, you need to actually make the argument. And so here specifically is what I require you to do. You have to tell me, if you're going to invoke a symmetry argument, what is your line of symmetry? Now you'll notice there it is, y-axis. Right? I'm going to need to know what is the formula for your reflection, and I need to see it algebraically. Right? You got to write down that you recognize what is that reflection actually doing. I'm going to need to see an algebraic argument. I'm going to need you to state and be correct that the function is odd. And I'm going to need to see the algebraic argument, because why the function is odd is usually not immediately obvious. And sometimes it's pretty clear. Good news, that'll make the argument really easy to write down. But I do need to see the argument. Okay. And lastly, I do need you to state and be correct that the domain is symmetric. Now you're going to notice conspicuously absent from this list of requirements, you do not need to make an argument as to why the domain is symmetric. And the reason why is because that usually is pretty obvious, right? If it's true, it's usually pretty clear. And so writing down arguments for why your domain is symmetric, it's usually kind of formalities. And again, not really what this class is about. So I'm not going to require that. And so all of this that I have, you'll notice then, let's see here, all of this business that I'm scratching out in yellow, you do not have to give me any of that. I only wrote it in here in case students might legitimately not see why or believe that my domain is symmetric as claimed. So not required in a Math219 symmetry argument. Okay, yeah?
Sounds like a lot of steps.
Yeah, well, okay, but your alternative...
No, sorry.
Yeah.
The question was like, okay,
yeah.
if I'm looking at a problem,
yeah.
I'm trying to think on a time crunch, should I try and evaluate it or try and go down the path where maybe it works, maybe it doesn't?
There is absolutely a strategy question there, and I don't have any silver bullets for that. Other than, you will notice a lot of this, you can sort of see it happening, right? I look at this, oh gosh, I can't quite see it. I look at this equation, and one of the first things I notice is those even powers, and that kind of right away tells me I'm going to have the symmetry of that curve, and so eyebrow up, right? Oh, hey, whoa, hey. This could be a symmetry situation, right? So my very next thing is to think, what is that symmetry? What does that do to points? Minus sign on the x. And then I just kind of glance over here and be like, what is a minus sign on the x coordinate going to do to this algebra? And so you don't have to write it down to kind of you can look down that road without actually going down that road. Does that make sense? And so, I don't want to say always, and all exceptions granted, but usually you can scope it out pretty well without actually doing much work. Yeah. Okay. All right. So do make sure to give me full arguments on this. Now, there's another thing I want to point out, and this is not my fault. This is the nature of reality, the nature of the way computations work in the real world. You do have to be careful. There are lots of situations that are close, but not quite, with symmetry arguments. And again, this is a very delicate theorem. It's a very delicate argument. I'll say it this way. Every little bit of the requirements of this theorem critical, right? So here's the problem. Let's suppose that you're looking at an integral and it does not fit with the symmetry theorem. That means that there is no symmetry argument to be made. If you start working down the symmetry path, then the problem is that's not actually progress toward a solution. That's progress towards something. It's progress toward a dead end. It's not progress, right? So if the integral that you're looking at actually, there is no symmetry argument. If you've checked like 4 out of the 5 conditions and just didn't quite get there, none of that is actually relevant to a solution. Again, this is assuming that there is no symmetry argument. And so it makes it basically impossible for me to give partial credit on something like that. Now, if there is a symmetry argument and you get 4 out of 5, then you get a lot of partial credit. You get 80% of the partial credit for that problem, if there actually is a valid symmetry argument. But you just have to watch out. So anyway, that's why I'm saying be careful when you're going through and checking these 5 requirements. Be careful. Make sure, double check yourself, and make sure that you're actually right. Otherwise, again, you get stung pretty bad. Okay. Okie dokie. So here is an example. And This is an example of what well, this is a counter example, I guess I'll say. This is not what I want students to do, but you can see how a student might sort of be tempted by, looking at this integral and just kind of writing this down. All right, well, the domain's symmetric. That's nice. This function has an odd symmetry. Boom, done. Tempting. But there's just a ton of stuff left out here. Symmetric? This domain's symmetric? It's symmetric around which line? This domain's actually symmetric around 4 separate lines. So which one are you talking about? I don't know what this student meant. Right? You say this function here has odd symmetry. Well, it does have odd symmetry over one of those 4 lines, but it does not have odd symmetry over the other 3 of those 4 lines. So just claiming it has odd symmetry, well, I don't know what you meant by that. Did you mean it has odd symmetry over the one that it actually does, or did you mean it has odd symmetry over one of the other 3 where it doesn't? It's not clear, right? So, problem. So the student who writes this down has correctly observed that the domain is symmetric. This student has correctly asserted that the function is odd, and this student did not tell me the line, did not write the formula for the reflection, and certainly didn't go through any algebra to confirm that claim to oddness. So this student gets, it'd probably be 4 out of 10. So this is what I'm talking about here. All you gotta do, the good news here, is how easy it is to actually do these other things. You just have to decide, okay, what is that line? And just write it down. Right? Then you have to think about the geometry. How does that reflection actually work? And just write it down. And then give me the algebra on the oddness. It's not like it's hard to fill in all 5 of those things. Okay. Here's another example. So, again, I don't encourage you to spend a lot of time trying to prove that the domain is symmetric. But if you just draw the lines, draw the curves, again, usually if in fact the domain is symmetric, usually it will be pretty self-evident by casual glance that it's symmetric. Okay. Is that cool? All right. So again, you got to tell me about that symmetry. You do not have to explain why. So I'm going to scratch this out, just because it's not required. I put it in there again, just in case you don't really quite buy it necessarily, and you want a little, guidance on how to see that this symmetry is true. Okay. And then let's see here. What else have we got? We have the symmetry is going to be over this line. Oh, come on. There we go. Symmetry is over that line. Stated, right? You're going to have to give me the formula for reflection. Now, this one is a little bit weird. How do I see the formula for reflection over that line? And I claim that the reflection of this point is this point here. The way I think is easiest to see that is to draw what I would call a little rectangular frame for that point. And it's pretty easy to see how this frame itself reflects, because horizontal, when you're reflecting over a 45-degree line, horizontal becomes vertical and vertical becomes horizontal. And then again, you can just kind of look at the picture and see, okay, well, whatever this positive amount x is, how far you go horizontally to get to the point, that's how far you go down to get to the y coordinate of the reflected point, etc. And that is I think this is a plenty sufficient argument to give in support of this formula for the reflection. Now, this is a good one to keep in mind, but every one of these examples of how to find the reflection formula is different. The geometry is just always different. But here's the good news. There's only so many lines, right? And it's, I think, a reasonable exercise to write down the commonly used lines, like the y-axis, the x-axis, this line here, that line there, right? Most of the time, again, not going to say all, right? But these are heavy players. These are the line of symmetry in question in a lot of cases. And so it's a good idea to have already thought some of those through, such as, for example, this one. I'm not suggesting that you memorize those reflections. Again, you have to make a reasonable case, right? But I think it's a healthy idea to have been through the calculations so that they'll make sense as you do them. Okay. Let's see here. The function is odd. How do I know the function's odd? Well, we have our reflection. I plug in my reflection into my integrand. And again, algebra, and you got to pay careful attention to your minus signs, right? That's squirrely part of this calculation. But if you go through and check it out, sure enough, what you find is that the value at the reflected point is indeed the negative of the original value. Okay. Everybody happy? Okay. All right, and so victory. Integral 0 by symmetry. And again, this could have been a really ugly calculation, right? You look at that domain, it's pretty weird. I guess I could think in terms of a change of variables that would turn that, rotate it, but then, I don't know. I feel like this could be unfortunate, and I feel like this is a much better answer. Okay, here's another one. This is a landmine question. Really easy to mess this up. Let's focus for the moment just on this question as stated. You look at this triangle, you can kind of see it in your head. There's a -1 and a +1, and hey, it's pretty clearly got a symmetry to it. And then you look at your integrand. Your integrand here is y cubed. It has an odd exponent. So it's odd, and the domain is symmetric, and it's pretty easy to see daylight and just think, boom, 0 by symmetry. And again, this is the landmine. Not only is that argument not valid, because there is no symmetry argument, but that's not even the right answer. This integral isn't even 0. So if you make a symmetry argument, however much of the symmetry argument you claim to have gone through on this question, it's progress in the wrong direction. It's progress toward a dead end. It's not progress toward a solution. So this is nothing. Does that make sense? So please don't step on the landmines. As much as I love symmetry arguments and super powerful, and you should use them and you should benefit dramatically from them, they be careful with the dangers. Okay. All right. There's a three-dimensional version. It's exactly what you think it is. Same idea. In 3 dimensions, we don't reflect over lines. We reflect over planes. Right? And reflecting over a plane, it's exactly what you think. It's exactly what happens when you look in the mirror. Right? Arguably the most relatable form of a reflection is the 3-dimensional reflection through a plane. Right? Every morning in the mirror. Again, oddness. Odd means that reflection gives you a minus sign. Right? Symmetry means exactly what you think it does. It means it is its own mirror image. Right? It is its own reflection. All that's totally relatable. Theorem, exactly what you would hope. Again, it's the same theorem, same 2 conditions. Integral 0. Again, you have to check both conditions. Be careful with that. Again, it's got to be the same plane. Exactly the same as the 2-dimensional version of the theorem. And so let me give you a quick example of this in action. Suppose, here I'll zoom in a little bit more. Suppose we are looking at our domain being the unit ball. By the way, the unit ball is a fantastic domain if you're thinking symmetry, because it has tons of symmetries. The unit ball is symmetric through every plane that contains the origin. Tons of options, right? Let's see here. I claim that this reflection makes the function odd. You can even see the algebra because I plug in this reflection specifically, and sure enough, as required, I get odd because of that minus sign. And so the integral is 0 by symmetry. Boom. Everybody happy? And just for fun, let's think about what a nightmare this question would be if I didn't use a symmetry argument. I guess I could use spherical coordinates, but that's going to make a lot of trig show up. Not that that can't be dealt with, right? But it's just kind of a pain. And so this would be heavy on the trig integral, even if you did it in spherical coordinates. Symmetry is a snap. Everybody happy? Last thing I want to show you, where I did kind of pull a rabbit out of a hat here, where in the world did I come up with this formula for the reflection? Or I guess more to the point, how did I decide to use the XY plane? And why couldn't I have used the XZ plane or the YZ plane or the plane Y equals X? Or there's a bazillion planes through which the ball has symmetry, right? So why did I pick this one specifically? And it's because while the domain is like just bonkers symmetric, right? The integrand's not. The integrand's, I believe, only symmetric through one plane, right? And so sometimes what'll motivate your choice is the domain. On the other hand, sometimes what should motivate your choice is the integrand. And now if I look at this integrand and ask myself, wait a minute, I know I'm going to have to go through some sort of a calculation like this. What do I want to happen in this calculation that I think will make this work out the way that I want? Namely, I want this precious minus sign right here. How am I going to get that minus sign to show up? And I'm looking at these exponents and I'm seeing two even numbers and an odd number. And I'm thinking, you know what? Wouldn't it be nice just trying to get this to work out the way that I want it to? Wouldn't it be nice if my reflection just put a minus sign on my z coordinate? Right? So in anticipation of the calculation, I actually wrote down in my mind, this formula for the reflection first. Right? I wanted this calculation to work. That means I wanted to have a minus sign here. That means I wanted to have a minus sign here. And then having made this wish list of I would like my reflection to be this, I then kind of said, okay, what plane do I have to pick to make this the reflection? And again, you just have to kind of think through the geometry of the picture and what would you reflect through to make the z coordinate the negative of what it had been, and that's the xy plane. Anybody see that kind of strategery there? Right? Sometimes this is how you make the right choice. Okay. All right. Okay, so moving along, we're going to make a little bit of progress. Actually, we'll see. Let's be optimistic. We might conceivably finish 5.6. This is just a bunch of applications. These applications are good things to see, but let's not forget that this is a math class, not a physics class, right? So I do get to kind of move a little bit more quickly through a lot of this. I did write down in the notes here a bunch of stuff that I hope you'll find helpful if you want to go through and understand the physics a little bit more thoroughly. That's great, but you don't have to. So I'm going to start off, as the book does, with a math application, which is to compute the average value of a function. We're going to start off with an idea called a weighted average, which I'll motivate momentarily. Here's just a plain old, regular old average. There I'm averaging these 6 numbers. Right? Notice some of those numbers are repeated, though. And so with that noticed, right, I can kind of stretch out this 6 as a bunch of 1s, and then I can kind of, sort of, if you will, kind of pair up some of these parts of what we're looking at. I don't want to call them terms, but you see what I'm doing here. Right? Kind of group them together like that. And then notice, when you have repeated terms, as I see in this calculation here, notice what you're doing is you're adding up in your numerator, you're adding up a bunch of things that look like that, and then in your denominator, you're adding up these things like that. And in particular, notice what you might call the multiplicity. How many times did the 4 appear? That 2 shows up in 2 separate places, one in the numerator, one in the denominator. Likewise, the multiplicity of the 7 shows up in the exact same places. The multiplicity of the 8, how many times did the 8 show up? Shows up again in the exact same places. Right? So what we have down here then is just a kind of a convenient way to summarize this kind of convenient grouping of just the arithmetic that I'm doing in averaging numbers. No tricky curves. Right? This is just notation. So with that observed, then the observation to make is, okay, well, these things that I'm momentarily calling multiplicities, like this 2 here, yeah, they are multiplicities. They are counting how many times something showed up. But once you've got it written algebraically, notice there's nothing about this expression here that suggests that these multiplicities have to be integers. Right? When you count, it's always an integer, right? But these kind of should be allowed to be kind of anything. Why would I want to restrain myself? And so instead of calling them multiplicities to suggest that they should be integers, we call them weights to free us up to, kind of count numbers with arbitrary weight, not with just integer. So why do we care about this idea of a weighted average? Well, for one thing, this is how your course grade is going to be computed in this class. So don't forget, if you look at on the class website and the course website, right, there's discussion of weighted averages. And so just as an example, now the numbers here are not entirely consistent with this actual course. Notice that these weights, a little different from our weights, right? Our final exam is only 30%. And there's also the business about attendance, and there's also the business about homework, right? Okay, I just wanted to keep the numbers relatively simple. You put those weights in place per that formula. And let's see, well, what does Bob get on the various exams? Well, Bob's grades were given as these numbers right here. Okay, well, you pair them up with their weights and plug into the formula as written here, right? And we get that is Bob's final course average, right? That's his weighted average for the course. And so, of course, that's really close to 3.0, so Bob gets a B. That make sense? Okay. All right. So, okay, why do we care about weighted averages? Well, we're going to kind of build up towards an actual physics application here. Next thing I want to do is talk about how to do weighted averages over functions instead of just lists of numbers. And if you think about it, a function is a bunch of values, and you could want to average a bunch of values. The only problem is that a function is not just a bunch of values, right? It's infinitely many values. Right? It's a whole curve of values, you might say. So the big idea when we say the average value of a function, we're going to use size in the domain as the weights. And with that said, notice I'm using otherwise the exact same formula. Let me get rid of my mass from the previous example. The exact same idea for a formula. Let me color code also a little better. That and that, not that different. We're still adding up. We're still looking at the values that I'm going to average. We're still multiplying those by the weights. Keep in mind, size in the domain. dx is the weight. Right? And then I'm adding up the total weights. Well, again, size in the domain. So this is just a copycat of this existing idea of a weighted average. And now, once you've noticed that, then oh gosh, where's my eraser button? There we go. Once you've noticed that, there we go. Of course, this is just b minus a. That makes it a little bit easier to remember, if you like. So we have this formula here for the average value of a single variable function. There we go. And this example down here is just plug and chug. I'll let y'all read that example. It's just literally plugging into that formula. Now that was a single variable example, but again, taking this same idea, size in the domain being the weights, I can do that in a double integral context as well. If I have this multivariable function defined on R2, well, size in the domain being the weights, this is what that idea of a weighted average turns into. Size in the domain, area, being the weights. Everything else is just kind of reinterpreting. What do we mean by adding up? Right? And copycatting that previous formula. So again, this turns into a nice, convenient little, again, that denominator is clearly the total area. And so nice, handy little formula for how to find the average value of a function on a two-dimensional domain. And again, it's very pluggy-chuggy, right? You just need to know the area of your domain. Okay, cool. If your domain is the unit disk, there is pi. Right? And then all that's really left, the only sort of work in some sense, is to do the double integral of the function. And again, details. Yeah?
Could you give me a practical interpretation of what that would mean?
Yeah, so, I mean, something geometric, maybe?
So, you mentioned, the mosquito example in 10. I'm just trying to think of,
Yeah, sure. Well, so, let's see here. I'll say a practical. I mean, something relatable. If I thinking about population density, what's the average population density, right? The average population density, well, that's very high population density in Manhattan, right? Very low population density in sort of north central New York, right? But average over all of New York, right? You would compute the average population density with this formula right here. And it turns out to just be total population over total area, which again kind of tracks. That is kind of satisfying. Does that make sense? Yeah. All right. Okay, so physics. We're going to describe something called center of mass. There's different ways to think about this. I'll say a couple of words about a more physicsy point of view on this in just a second. But center of mass is a weighted average. So, I mean, from a physics point of view, this is why we're interested in weighted averages. It helps us compute center of mass. Specifically, it's the weighted average of position. So now, just as a starter example, if you have a couple of masses, right? So you have a small mass there and then a large mass here. What is the center of mass? Well, weighted average. Here's our formula for weighted average. I'm going to use the masses literally as the weights. So there's my first weight is the first mass. Second weight is my second mass. And again, as claimed, we're looking at a weighted average of position. And so x1 is the first number that I'm taking an average, a weighted average of. x2 is the second number that I'm taking a weighted average of. So literally a weighted average position. Now, why would we be interested in such a thing? And here's where physics kicks in. And again, this isn't a physics course. But if you want to persuade yourself, you can totally work out the mechanics of this on your own. But this point, the weighted average, the center of mass, it's the balance point. It's where if these two masses were connected by a, some sort of a massless, let's think a little teeny tiny piece of balsa wood, that kind of thing, right? This is where you would put your position to have the thing balance. Okay, and you can prove that for yourself. Again, if you want to do the physics, just compute the total torque. The total torque, if you put your finger right there, on the one hand, this big mass is going to create some torque, what you might call clockwise. This little mass is going to create some torque that you might call counterclockwise, and those will balance perfectly. All right, but again, this is not a physics class. Oh, and this is an out-of-time class. Yeah, we're out of time, so we will pick up here later. We didn't quite finish 5.6, but we made good progress. See y'all later. Have a great weekend. See you Monday.